Hey, good morning to all of you. And we have a Rob Farber, who is a chief scientist at the Black Dog. So just to introduce him, he's recognized for his work in high performance computing, machine learning, scalable algorithms, massively parallel computing devices such as GPUs and Intel Gen 5, complex dynamical systems, and high energy physics. He has co-founded two successful companies and currently acts as a consultant to Fortune 100 companies. His recent work has included achieving 13 petaflops per second average sustained performance on the Titan supercomputer, plus the fast graph algorithms for social media, needle in the haystack problems using NVIDIA GPUs. And Rob also served on the external faculty at the Center FE Institute and authored CUDA application design and development, which I believe most of you might have read that book, with the follow-up book in the development. As an author, teacher, Rob has 100 plus peer-reviewed scientific publications. So welcome, Rob.
Thank you very much. It's a pleasure to be back here at GTC. I've been very lucky to speak at pretty much all the GTC conferences so far. And I see friends that I've made from teaching and speaking around the world and around the country and in the audience. It's lovely to see all of you. Thank you very much. So last year at GTC, I had the luxury of having two one-hour talks to present at. And at that time, I showed you how to do essentially scalable machine learning, getting 700 to 800 gigaflops per second out of a single K20 CPU, and scalability to large numbers of GPUs. Well, that was in my Hello World to Exascale presentation, and what I would like to kind of do a quick review on that is here's a Hello World C++ program. Then we do some form of initialization. We then can, for example, perform an optimization using a canned optimization routine on an objective function, working on a function of interest. Over in the green column, you see how we're essentially doing a function transform reduce. You saw that in my CUDA application design and development book. You see the OpenMP parallel pragmas. So what this does is it allows us to run with OpenMP on the multi-core CPU and get good performance on that. Well, for GPUs, you see that what lit up in the yellow in the blue box is the OpenACC data pragma, which essentially just says copy the parameters over for the optimization and then conditionally copy the data for the examples, meaning I only have to copy them once. So I'm able to minimize my data movement. And then, of course, I can provide and that moves the data over to the GPU for me, one or more GPUs. Then I can add an OpenACC parallel pragma to actually do the computation on the GPU. Exactly the same as traditional OpenMP programming, very simple and concise. And at that point in time, you now have a code which I like to congratulate everybody because you are now Exascale capable. In fact, in my classes, I provide the code that actually generated these results, which on the Oak Ridge National Laboratory Titan supercomputer achieved 13 petaflops average sustained performance. That's average sustained. So it's not peak. That's the average that we see over a reasonable runtime period on both a linear and a nonlinear problem. If you look at my presentations from last year, you see that the NVIDIA GPUs actually increase in performance on nonlinear problems, which we love because the world is nonlinear. So acknowledgements, thank you to Fernanda Fortier for helping me get the time on the Oak Ridge Titan supercomputer. So notice that's 13 petaflops on 16,000 GPUs, which is only still a portion of the machine. There's minimal performance variation. So in the red line that you see dropping down, that's the variation that we see, which is why the average sustained performance is so critical, because you have network traffic and latency when you get to large problems, in this case 16,000 GPUs. So Titan was designed to be a 20 petaflop system. As I mentioned, I was not using all the GPUs in the system. Plus, my hope is to do an OpenACC run, which will actually achieve the full throughput of the Titan supercomputer of 20 petaflops per second. This is, again, code that you will see and be able to work with in OpenACC, just like with the Hello World program that I just showed you, by running concurrently on the CPU and the GPU at the same time. If you look at my current Dr. Dobbs OpenACC tutorials, they're freely available, you can actually see how I mix and match between CPU and GPU in those tutorials. Moving quickly along, I also always stress report on honest flops. Include communication overhead and computational latencies. Don't try and sandbag your audience. So there's the link to, unfortunately, it's an Intel Xeon Phi article because I also do comparisons and get 2.2 petaflops using 3,000 Intel Xeon Phi on the TAC Stampede supercomputer. But you can get the source code there. You can also contact me to get the source code. Like I said, I use it as a teaching tool. So the one thing I really like about the GPU execution model is that we limit communication in the threads to essentially one thread block, and all the blocks run when those dependencies are resolved. So the nice thing is if I'm a card dealer, essentially having those thread blocks, if I have one person like Michael here sitting up front reading his email, I can toss him a card whenever he's done reading email and he can raise his hand. Or if I'm dealing cards to everybody in the audience, then I can, anytime someone raises his hand, I can toss one of those thread blocks out to them and they can start doing useful work, which is the reason why you can take your CUDA executable, plug in a new GPU, and you don't have to recompile, but it will start running on those much larger GPUs. So I call that a strong scaling execution model. And it's very important that we exploit that in both C, Fortran, and C++ to get good performance. Here I'm showing OpenACC pragmas in each of those different languages. So the nice thing is that OpenACC I've actually seen at the PGI booth where they've taken a single OpenACC code compiled to run on NVIDIA GPUs. That's great. I've also seen them, that same code compile and run on Intel Xeon Phi, AMD, ARM also with a different vendor. And there's a number of different OpenACC implementations out there, including I wrote a recent scientific computing article about the about the GNU OpenACC version that will be coming available. So there'll be a freely available OpenACC compiler in the near future. So this is not necessarily just an OpenACC talk, but I have so much material to go through. So one of the questions that we have to work with in social media and pretty much any big data project is how do we work with complex data structures like graphs? Well, first off, we need to create a dynamic data structure that can handle those complex data structures. It must be performance robust, meaning we can't sit and lock and wait on one particular region of memory. We need transparent host and device-to-host access. So we have to, pardon me, we have to be able to create our complex data structure, say like a graph with all the attributes on the host, then do our parallel computation on the GPU, and then work with it on the host to report the results. Standard workflow. So we need a massively parallel stack that is low weight that will transparently move and manage our data for us. So, and I point out that a stack is required for dynamic parallelism because the whole idea behind dynamic parallelism is you do variable amounts of work, which means that you have variable amounts of data that you need to report. So dynamic parallelism equals variable output. Apologies if I'm speaking quickly. I have a ton of material to go through. So you can also download my slides after the presentation. So following is a very fast introduction for how to create that massively parallel stack that I just talked about. Well, the first thing is that you need a parallel counter that will not exhibit pathological behaviors. For example, the NVIDIA SDK for histograms is really nice. The problem is it assumes a uniform distribution. If you start nailing on just a few different histogram bins, performance degrades fairly badly. So you can't afford that with a massively parallel data structure, so even pathological cases where every thread increments at the same time has to be fast. So looking at that, I say that atomics are great, but don't use them because look at the serialization. We do atomic adds and we 1, 2, 3, 4, and it's very slow. But there's much faster if there's no contentions. For example, if I have a warp and I go through and I do an atomic add, well, everything gets incremented at the same time. There's no delay. So the beauty is that if you structure the computation so you have a minimal overlap, say if you do a mod by the warp size on a parallel counter, you can exploit the atomic nature of the atomic increment, get very high performance, but you still get the full speed when there's no contention. So then what I do is on my parallel counter, you can sum the locations. So it's just a serial operation, but you're not going to be reading a parallel counter while you're incrementing it at a parallel, at least, and expect consistent results. So here's the actual C++ code. It's very simple. I highlighted for your eye viewing to see that we actually have a count array of integers in this case for our parallel counter. And if we set n atomic to 32, it means that we basically have 0 weight when an entire warp is updating the parallel counter. Well, it works great on multi-core Intel Xeon Phi as well. For example, if you're running just with a few threads, you can do a randomize, for example. That's an easy way to do it. Here's performance results. So what you see is in the purple line that's going straight up is just a simple atomic increment counter on a Fermi GPU and performance higher runtime is bad, that it just blows out really quickly. And that's not so good. The NVIDIA guys, kudos to them. They actually did some really nice work on Kepler, putting the atomic increment in the cache, and we've got much better performance. But if you use this parallel counter, you run fast on both the Fermi and Kepler GPUs. So it's definitely the way you want to go, the way you want to build your parallel histograms. So how do we do transparent data movement? Well, you need to have object layer layout compatibility. So basically, you have to be able to transfer a contiguous region of memory and have it be on this, be the same structure on the host and the device. And that's not mainstream yet. So what happens then is that you move your host and over to the host. Your structures don't align, and everything falls apart. Not so good. Happily, it was addressed by the C++ Standards Committee, which was really created before GPUs were a factor in computation. And they set up for binary compatibility for file I/O and socket I/O. They have something called is trivially copyable, so that you can do your transport of a single contiguous region and everything works. So you're going to have to use that whether you're using unified virtual memory or this parallel stack. Again, I'm short on time. I usually spend a lot more time on this. But basically, there's a couple calls called ispod, so you can check if your data structure or your C++ structure is fine, is standard layout, and the most general is has trivial copy. I recommend that you look at these. They're part of the C++ 11 standard. Sadly, there's no C++ 11 compilers for us, but the GNU guys and the PGA guys have front-end interface calls that we can actually call and to just check if the structure's okay. That's not part of the mainline execution code. It's just for a check. Okay, so it works well, and once you get your code working, you can actually comment it out. Do the data movement. Here's the parts 28, 27, 26 of my Dr. Dobbs tutorials talking about all of this, so you can take a look at that. And with CUDA 6, it's to be determined how well managed memory will work for us in performance, so we'll take a look at that. So what we can now do is combine 1 and 2 to act as a stack that provides fast object allocation and transparent data access to both the host and the device, and can handle arbitrary number of inserts efficiently. So if we look at the allocation time of the GPU, the CUDA malloc is heavyweight. And the point is, it's only going to get slower. It's got to manage more devices and more complexity. So the solution is you allocate and do a bulk alloc. Okay, not really rocket science here. But if we take a look at the times, well, you can get your bulk alloc in basically 17 microseconds as opposed to 7.86 seconds if you're actually doing one individual mallocs of one C++ structure a million times. So you really want to do bulk allocation. Now what you do is you modify that parallel counter so that what we can do is increment essentially our location in that bulk memory location, so we get the benefit of that fast atomic increment. So how do we do this? Well, what we do is we essentially assign each integer counter in the counter array to point to a unique memory location. Okay, we've all played this trick with two-dimensional indexing. So counter 1 indexes from count 0 to max count minus 1, and we partition it across as you see. So what then happens is we've got our individual locations, and the allocator just grabs the first one that it can, depending on the thread index and how it goes. So the allocations are irregular. There's a scavenge operation, so once you start getting full, then it finds a free pool, so you can go and grab the actual amount of the actual free location. Okay, so now you see how we can enable transparent host to GPU, multi-GPU, complex data structure management through a massively parallel stack. The code is actually pretty simple, straightforward, and it's quick. So take a look at part 28 of my Dr. Dobbs tutorial series, and that'll show you how to do it with working code. Now, I'd like to actually break a conception. Is most people think that GPUs are only good for big computations. And actually, if you take a look at it, you have all those processing elements that you need to keep busy. Well, the sound effect is to reinforce the point that no, they're good for many small problems too. They can actually, as long as you can keep an SM occupied just like a core on a multi-core processor, you're going to get extraordinary performance, and I'll show you that in a production code here in just a second. So First off, we can now change parallel counter to be an accumulator, but we can run with it in this multiple small, using one SM as a core mode. And usually what we want to do is we want to essentially create a sum on a bunch of different vectors at one time and have our different sums. That's a common use case that we want to work with. Similarly, there's the actual code, and it works quite nicely. I just plugged it into a production code I did for Cold Spring Harbor, and it worked beautifully. Same thing, you can also do parallel concurrent sorting in the exact same way. And here's the actual code for a bitonic sort. That's the step where we continue iterating to do the sort using essentially function invocation on the GPU. And here's the calling method. So there's the actual full source code for a parallel bitonic sort that you can run in streams. And I'll show you performance results in just a second. So now, what does NVVP look like when you start running these many different concurrent operations, essentially one per SMX as a multi-core processor? So what you're seeing is 15 hyperq threads all running in parallel, issuing a parallel bitonic sort. The first thing I observe is, hey, that's a really nice scheduling trapezoid, because there's going to be a little lag as each kernel starts up, but then everything runs. So NVIDIA did a great job with scheduling on that. I'm very impressed. The second is if I compare this to a simple Q sort, you see the lower density of operations with NVVP, and not surprisingly, we find that recursion is expensive. So you really want to continue looking for iterative methods inside of these small kernel execution environments. And here's some numbers. Simple bitonic sort on 10,000 floats using 15 streams on a K40 took 4.5 milliseconds using this absolutely simple bitonic sort without any sort of shared memory optimization or anything else like that. And the simple Q sort took significantly longer, 60 times longer. So it reinforces the point. You want to do iteration. So let's now look at how we actually apply this to our computations. So this is a project I did with Cold Spring Harbor, and it's an analysis pipeline. Essentially what we're doing is a statistical bootstrapping procedure to find the significance of oh good, I'm actually moving quicker through the data, through my slides than I needed to. I can slow down a bit. So we're actually looking for the significance of some peptide measurements made with a mass spec, and we want to actually find out then, is this actually occurring by chance, or is it actually a real signal that we're actually looking at? So we use a statistical bootstrapping technique. There's lots of heterogeneity, variable sampling. The instruments report different results, a lot of noise in the system. So how do we figure out what can we trust in those actual distributions that we're working with? The point of contact is at Cold Spring Harbor's John Wilson, Dr. John Wilson at Cold Springs Harbor. And it's very important to research for disease and others. For example, you can see a healthy lung versus a not so healthy lung caused by disease. So the whole idea is to search and find out where the peptides, where the proteins have changed, so that we can fix them. So the key point with this is that people do look at an overall measurement, and then they take this work and they go out and they do 3 years of work, and they'll spend lots of money doing the research. Okay. And then they go and they come back and they say, well, I'm not seeing what I'm expecting to see after 3 years of work. And that's 3 years of someone's life. Okay? And then they go back and they take a look at the distribution that they initially looked at. And oops, okay, if we look at the variability, we actually were probably looking at noise. Okay? Think of yourself in that position. Ow. Okay, I just wasted a lot of money, professional reputation, and many years of my life spent in the laboratory. So you really want to make sure, which is a key point I made in my last year's big data presentations, that validation is key. So for example, I show you in last year's presentation how to do computational drug design, at least the first part of the steps, using machine learning, where we would predict protein binding affinity. When we then went to get funding for the company, the executives came back and they asked a very simple question. They said, how do we know that you're not playing expensive computer games with our money? And we had to do essentially a double-blind test. Well, this is the same type of a thing as you need to ask the data, how do I know that you're not just feeding me a bunch of noise and that I'm actually seeing a real signal, which is the reason for the for the Cold Spring Harbor analysis pipeline. There's going to be, it's grayed out, there's going to be a public URL forthcoming. This is going to be a production GPU system using these multiple concurrent kernels. And basically, the point is that you get a number of different p-values, you sample those, and you do essentially a statistical bootstrapping method, excuse me. And if you see if you're 95% certain that it's good or not. And here's actually a NVVP timeline running on a K40 plus a K20C. And what you see is 15 threads running 1 per SMX concurrently on a K40 GPU. You see 13 threads running concurrently on a K20 GPU. You see that there's variable lengths in the colors. The coloring does this pointer work? The coloring of these kernels, this is one thread executing a task, a single task. So this might be one single task, then it finds out that it's done, it can do another one, so here's another one, and so on. Some of the tasks have regions, because they're data dependent, they can take a really long time, on the order of sometimes 16 seconds. So the data is completely variable. The runtime is completely variable. So actually, what the control loop of the code is an OpenMP loop with a schedule dynamic 1. What the schedule dynamic 1 means is that any thread that is available for scheduling, I will put something on, and if a thread is busy, I won't try and issue work on that schedule. We then go into essentially the task-based computation that essentially just asynchronously launches all the different kernels that we want for the task. So we initialize our parallel counters, we do the peptide calculations, we do the protein calculations, we do the sorts so we can find the median values, and then we do a report which writes a small amount of information to map to memory. So it's a very low output, latency tolerant way to express the data to get it back to the host. And inside of that work loop, the task level parallelism, which is just like programming a task in OpenMP, I just go in, and after the first kernel starts, I set a event. Then I go through continuing issuing the asynchronous kernels till the very end. Once the kernel starts in that task, the event wakes up, it returns back to the OpenMP loop and says, I'm ready for more work. And that's how we get this really nice load balancing packing of work very tightly across all of the GPU. And I'd like to thank Justin Lupkin, if I got your name right, at NVIDIA. NVIDIA's been very supportive and very helpful in moving this work forward. Also, because we're pressing the limits in drivers and resource utilization. This is going to be a 24/7 type of a production system. So we're trying to pack these kernel launches much tighter and to make sure that we have full performance across the entire run. And Justin has been very important in helping with that work and will continue to be so. So I put you on the spot, Justin. Thank you very much. So that's one type of problem that bioinformatics chemists need to approach and work with. Good. And so here's another application. Again, fitting in the point that you have a distribution of data. You have essentially your samples. And was that a... can I keep going? Okay, good. So what you do is you have a bunch of samples of data, and you need to see what kind of distribution does it fit. So this is a product that I've been working with. It's called SurveyFit. It solves every distribution in a library. So for example, if you're fitting a normal distribution, you need to fit where the mean is and the standard and the variation, okay? So you fit that, you get your best fit. You do it for a couple hundred other additional distributions, and then you do it. You do that according to a number of different fitting techniques and goodness of fit measures. And then at the end of the day, you come back and there it is. And you rank everything against everything, and it gives you your results back. So most bioinformatics people don't want to work with computers. They don't care if you're running on a GPU or a CPU. But they need this massive parallelism, and they need the performance of the GPU so that they can just feed a data set into it, have it run, and come back in a reasonable time to give them a sorted value of numbers so that they can actually go in and take a look at the distributions and see, hey, is this noise or is it not, and what is the best distribution fit? In future invocations, it's possible to do multimodal fitting as well, which is very computationally expensive. So another project I've done is Purging interpolation with a company called MapLarge and graph algorithms with a company called SysTap on the DARPA X data. So Purging interpolation is heavily used by the Air Force and GIS systems. And it's basically a way of reducing a large amount of data to a small amount without losing detail. Okay, and so you can see, for example, if you do just the polynomial regression, it actually looks nothing like the map whatsoever. I'd love to talk to you about the graph algorithm work that we did. Sadly, there's no time, so you're going to have to go to the MPGraph GitHub repository, and you can take a look at the work there. And there's comparisons with Intel Xeon Phi as well. So parallel Purging, basically what we do is we have to estimate the semi-variogram. We use Magma for that. Magma exhibits strong scaling for that solver. It's really nice. Then what we do is we're essentially doing a massively parallel fit across of the Purging results call. So it's a two-dimensional call. So what we can do is we do a parallel implementation. It works quite nicely. And here's the timing. We get 55 times faster than a quad-core Xeon. And that's with SX acceleration. The nice thing is we can plug in an extra GPU, and it exhibits strong scalability. So basically what we can do is we can get 2 GPUs 2x faster, 4 GPUs 4x faster. And that's part of the point that I was making in my previous presentation, that we're going to see the migration from the GEMs, the twin combinations of GPUs, to 4 GPUs, 8 GPUs, and beyond. Very quickly, do I have 15 seconds? This gives you kind of just a view of the distribution, and if you're looking at the different fits, those are different ones in the libraries, so you see the distinction and why you actually want that. So thank you for your time and attention.